Thanks, Vasco. And, okay. So today I want to talk about some work in progress I'm doing with Jean-Elias Guerrieri and a PhD student of his, Mehmet Gurus, about the smart root of FFT filters, which is something that we've worked for a long time already. And the subtitle of the talk is Bridging Bootstrap with Positivity. Since you already have many talks during this conference about positivity, let me try to make an effort to bridge the two fields and try to see what we can do. Right? And, okay, so here are some references I will mention later. So, the first thing I want to convince you, or I want to explain a little bit, is that sometimes interesting physics needs subtractions. Right? So you have a lot of problems with unsubtracted special relations, but interesting physics sometimes needs subtractions. And then on the other hand, even when you look for quantities that are accessible through unsubtracted special relations, one must be careful on how you take the weak coupling limit. Talk about weak coupling, give an example where things get complicated. And then, in the last part, I will show you some slides, and I will talk about the space of EFTs with a cutoff. With a cutoff. Okay, so the motivation to look for quantities that need subtraction comes from LHC. Okay? So there is something called BSM physics that you already all heard about it. And in the standard model, usually you write a Lagrange that contains operators with dimension less or equal than 4. But then the first correction that are expected in the effective field theory are operators of dimension 6. Well, for dimension, I mean the canonical dimension of the operators in 4 dimensions. Plus, eventually, operators of higher dimension A, plus dot dot dot. And as you can guess, the one that will be likely accessible during our lifetime, maybe, are this correction here, coming from this operator of dimension 6, which are the lowest corrections. And I'm going to convince yourself that this requires subtractions. I will just review this. And in particular, our goal, so our main goal with trying to do this bootstrap, is to bound two specific operators which are related to Higgs physics. So Higgs physics. And the two operators, let me just write them for the sake of the presentation, are one which is called the CH, that has this form, and then there is another Wilson coefficient, CT, which has some some form like this, where H is the Higgs field, which is a scalar, a charged scalar under some global symmetry group that I can tell you more in detail. But, okay. So these are the kind of operators that are contained in this dimension 6 Lagrange. Right? But then we know, since we don't know what is the UV completion of the standard model, we feel that the best thing to do is not assume a lot about, for instance, the properties at the energy of this amplitude. So let's be as generic as possible. So if we are being as generic as possible, Martin, long time ago, told us that for very large energies and fixed T below the first singularity, the T channel, the scattering amplitude, if I divide it by S squared and I take this limit, this goes to 0. Okay? So the amplitude actually can grow to infinity. Right? Now, if we draw the usual dispersion argument, right? So imagine that with this scattering amplitude, I will comment about this later in more detail, but just let me give you a flash reminder that we expect some cuts, some range points, and so on. Okay, we want to write some dispersion relation of this form where we integrate along some contour and then we blow up the contour. We pick some contribution and then some arc at infinity. Right? And the issue is about this arc at infinity, this C infinity. Because now, if I want to extract, for instance, the Wilson coefficient associated to this operator, since there are two derivatives, right? What I need to do, I need to write a dispersion relation. So when I integrate on this contour, I need to write something like T of Z and T divided by Z squared in the Z. And now it's clear that if I write such a sum rule for this quantity CH, when I go up the contour, because of this decay, the integral over this C infinity will be divergent. Will be divergent. Right? So we cannot really block the contour, and then that's what we do. We usually subtract. So we put some factor that depends on some auxiliary point, that's 0. Right? So there will be some pole associated here. We integrate in Z, we block the contour. Right? But then the answer will be not given anymore in terms of discontinuity, but will depend also on the value of the amplitude on the additional point. So you lose positivity, basically. So you lose positivity. And this is explicitly written here, where the expression for CH can be found in this very nice paper by Laura Tazzenvicchi long ago. And here explicitly you see that there is some rule involved in some cross sections that I'm not going to spend time on it. But you see that there is a dependence on some constant, this C infinity, which is related to this integral on this contour. Right? And if this, okay, here there is also a minus sign that makes no positive sum rule, but the need of subtractions is related to this constant C infinity. Okay? That using only positive you cannot take an electron down, and therefore we need to use the full non-perturbative unitarity to put bounds on these quantities. Okay? So I think this is okay. So I will stop here about the motivation. Okay, so to summarize, what we want to do is that we want to access to quantities that require subtractions, such that this arc blow up, and we are going to use the full non-perturbative unitarity. Okay? Are there questions so far? Okay. Okay, so let me go to point 2. Okay, so now let me go more in details. Let me talk about a specific example of Bootstrap. Alright? Of Bootstrap, where we want to really bound some Wilson coefficients associated to some effective field theory, and the example that I will explain you in some detail is related to the effective theory of long strings that you can find in this very nice paper from 2 years ago, and that we already tried to bootstrap recently. Okay? So, just as a reminder, the effective field theory of long string, you can imagine that you have some worksheet in your embedding space. And you can imagine that on top of your worksheet, you create some bumps, and you make them scatter. So you make scatter these bumps on top of a worksheet. And this worksheet, you can imagine it, for instance, if you have in mind some confining gauge theory like QCD, you can imagine that is the flux tube generated by extending a pair of quark-antiquark up to infinity. Okay, so in absence of dynamical quarks, this flux will be stable and will create some long string. So the perturbations of this on top of this string can be described by an effective field theory, two-dimensional effective field theories, because it's a string. Right? So there will be some effective action. A effective, where we have the integral, then we have the metric, and then the first term is the usual Nambu-Goto because it's a string. Right? But then there will be correction because it's an effective field theory, we are in non-critical dimension. Right? We are like in generic D. So there will be some operator R, which is the Ricci scalar, and then some correction with some Wilson coefficient, R squared plus dot, infinite correction. Now, what are the degree of freedom here? Right? So the physical degree of freedom are the transverse fluctuation of the flux tube in some particular gauge frequency, right? Which is called the static gauge. So in the static gauge, where the string is, well, from the name is static, okay? So it extends along one spatial dimension along the time. The degree of freedom are d minus 2, so we are like d minus 2 scalar, xi. And these scalars actually are Goldstone bosons, okay? And those are Goldstone bosons because, as you can see, the effective string, the action of the effective string must be compatible with Poincaré. The presence of the string breaks spontaneously Poincaré. Right? So, in presence of the string, as also was mentioned by the talk by Gabriel, we have the breaking, well, in this case we have only Poincaré, so we have the breaking of Poincaré to Poincaré on top of the worksheet times some additional rotation transfers to the string. And that's the reason why we have like d minus 2 possible Goldstone bosons. Right? Okay. So now we want to compute the scattering amplitude. Okay, when we imagine to excite this Goldstone boson on top of the string, we make them scatter. And the amplitude can be computed in perturbation theory for small momenta because it's an effective. So the amplitude for this for the scattering of these Goldstones, and let's fix, because I won't talk about jet dimension anymore. Let's fix d equals to 3. So we're looking about effective strings in 3 dimensions. And the scattering amplitude behaves like s squared times L string squared divided by 2, where S, I remind you, is the center of mass energy of these particles. Okay? So it's S squared divided by 2 plus. So this comes from some diagram, some contact diagram of this one. Okay, 3 level. Then there will be this term, which comes from the loop. Okay, so we can do some loop and compute for this Goldstone. And then, at 2 loops, we have some real contribution that we parameterize in this form. This is just, it's not important, just parameterization, but it's important to compare with the lattice result. See, plus dot dot dot. And this in principle really comes from a full-fledged 2-loop computation, but with the addition of some contact term. So, yeah, some counter term. Right?
This is the forward limit?
No. But you are right in a sense, because we are in 2 dimensions, so the angle is 0.
Okay.
Thanks. Alright, so the presence of gamma 3 here in this case comes because we have to add some counter term here to cancel the negatives. Alright, that's why there is this gamma 3 that's associated to this operator here. Right? Then dot dot dot. So what we want to do using the Bootstrap is to bound this Wilson coefficient gamma 3. Because as you see here, up to this order, the amplitude depends only on the string length. Okay, so the amplitude is universal up to 1 loop. Alright? And then, starting at 2 loops in perturbation theory, the non-universal corrections start to appear. So So in principle, each effective string theory that comes from a different gauge theory will have a different gamma tree. And what we want to know is that what is the allowed space for this gamma tree Wilson coefficients, right? Which somehow characterize the space. It's a projection of the infinite-dimensional space of all possible confining gauge theories. Okay? When we project them, when we consider them in this setup. All right? Okay. So this is the perturbation theory. Now, what are the properties of this? The non-perturbative properties of this sample? Because we want to perform some non-perturbative next time.
Sorry, can I ask a question?
Yes, please.
Is there a reason why there isn't some term dependent on extrinsic curvature in your effective field theory, which could come at a lower theoretical order, like the Polyakov type term?
Right. That's very good. Yeah. Right. Very good question. So in principle, in this lower order, there are two possible operators, R, and there is also K square, which is built. So this is the Ricci scale, and this is built in terms of extrinsic curvature. Right? But this term can be, with the redefinition of your fields, can be removed because it's proportional to the equation of motion. But this term R,
I see.
okay, this term R is a so-called evanescent operator, so doesn't produce any physical shift at this order.
I see. So, but let me make sure. So if I consider instead of p equals 3, higher dimension, would this change? Because
Yes, if you go to d equals to 4, for instance, then at one loop there will be still a universal correction, but it's what is called Polchinski-Stroniger.
Okay.
And then that will depend on the dimension with d minus 26. Okay, so this nice dependence, then into d equals 26,
Right.
everything becomes nice and integrable actually. You can see. Okay. So, thanks for the question. Did I understand the question?
Yeah.
Okay. So, now let me talk about the non-perturbative properties. So, as you can imagine, those are crossing, analyticity, and unitarity. Now, unitarity, so let me start with unitarity. So unitarity, it tells you that 2 times the imaginary part of the amplitude t must be greater or equal to a phase space factor times the absolute value square of the amplitude, which is a positive quantity. We all agree, but strictly speaking, this is the full unitarity. Now, you see, you can also write it in a different way, saying that this is the 1 over 2i, the discontinuity, 1 over I, the discontinuity in the S channel of the amplitude. So what unitarity is telling you is that in the complex S plane, for physical energies, when these particles can go shell, there will be a cut. Okay, and the discontinuity of the amplitude is related to the absolute value of the amplitude squared. Right? So since our particles are massless, because those are Dostons, the threshold is at S equal to 0. Okay? And then starting at S equal to 0, there will be a cut along the real axis. So this is unitarity. It tells you it's like a branch point and there will be a cut. And then crossing, so we have T here. Crossing will tell us that T evaluated in the S channel must be equal to T evaluated in the U channel. Okay? We don't have T channel because we are in 2 dimensions. And U is minus S. Okay, so crossing is telling us that T evaluated here will be equal to T evaluated here. Right? And then, as a consequence, it also tells us that there is like some left cut. Okay? And that's it. So this is about crossing. Then there is something, some other property we can use, which is called real analyticity. Just the fact that the amplitude here is the complex conjugate of the amplitude on the other side of the cut. Alright? And then analyticity is the easier. Once we specify all this structure, it's easy because it just tells that there are no singularities in the complex plane. Okay? So the sample is totally analytic in this complex plane. So this is the non-perturbative structure. And now, using this part, and using this low energy expansion, we can start to write some rule, for instance. Okay? So let me erase here. And we can write some rule. So let me write some rule. So you see, what you want to do basically, you want to integrate along this contour your amplitude weighted by some function, right? Some coshicant. Want to integrate on that contour. And for instance, we can write some rule for the first Wilson coefficient that appears here on the amplitude, the total S square. So the sum rule would be something like 2 over pi integral from 0 to infinity. So I'm not doing the exercise explicitly, but you can recognize this form, I guess. Because 1 over s cubed is because we want to extract the second derivative at threshold, and okay, the imaginary part because we are integrating along the cut, and we can neglect the contour at infinity because there is a 1 over s cubed here, so it decays fast enough. So this can extract the second derivative, right? It will tell this term, and this is positive. Okay, so this triple n square is positive. It's a good thing. But now let's try to do the same for gamma 3, but being honest. So really take into account the fact that there is this term here that is universal, comes from the one loop. Okay? So if we write this sum rule, we would end up in something like 2 over pi, the integral from 0 to infinity. Then we still have the imaginary part, but now we need to perform an higher subtraction. Okay? So we need to write s cubed over 16, and here we have like s to the 5. And the subtraction is needed because if we integrate the imaginary part from 0 to infinity with 1 over s to the 5, you see the imaginary part starts at s cubed, and then it would be divergent, this sum rule. So we need to perform this higher subtraction. This will extract our coefficient 2 gamma 3 minus 1 over 192, okay? But it's not positive. This sum rule is not manifestly positive. Not positive. It's not positive, and that's the reason why we want to perform the non-perturbative bootstrap in this case. Are there questions so far?
On the right part of the graph, you just started with a function which is polymorphic in the upper half plane. T is more than this, right? The conditions are the constraint.
I could not hear.
The conditions of analyticity, unitarity, and crossing,
Yes.
they constrain T more than being just polymorphic in the upper half plane, or it's actually because someone pictures in the.
So, unitarity in general, okay, here is massless more delicate, but unitarity in general,
Yeah, I know in general, but I guess in this case,
yes.
specific, is it sort of equivalent to having the function just of the upper
Yes.
half plane?
Yes, the short answer is yes. Okay. So now let me use this example just to remind you how the usual primal mathematics bootstrap works in in a very simple in this very simple setup. Okay. So to form this gamma 3, what we usually do is, as our friend said, is to use the fact that this function, all the information of this function are encoded just in the upper half plane. So the only thing we need to do is to map the upper half plane to the unit disk. Okay, so we take our function, which is defined in the upper half plane, and we perform a map from the upper half plane to the unit disk. Okay, so we choose some center in here, and the map that we use is we call it chi, is this function, and this chi is given by this form. It's called some Cayley transform. Okay, And this function, as you can see, when s equal to 0 is equal to 1, so it maps the threshold here, maps infinity here. Okay, the center is somewhere on the imaginary axis, and then the cut is mapped on the boundary of the disk. Okay. And now, once we perform this map, we can just Taylor expand this function in this disk. So we'll perform like t, we'll write down t as a sum up to n of some Taylor coefficient in power series of this function k. So this is how it works, and this parameterization, since we have mapped the upper half disk to the upper half plane where we already used crossing and analyticity to the unit disk, we just need to impose unitarity on this ansatz. That's the only thing we need to do. So if you want to, for instance, minimize gamma 3, we will write some problem where we ask some find the minimum, okay, varying over this AN of gamma 3, which will be given by a linear combination of this A con N, okay? Find minimum gamma 3, imposing, for instance, that 2 times the imaginary part of t is greater or equal to 1 over 2s absolute value of t squared. So we do this numerically.
Why is that crossing symmetric?
So crossing symmetry is manifest in this plane, okay, by the fact that on this side you have t, on this side you have t star. So that's crossing.
Okay.
And this map preserves this sort of real analytic structure, because now you have just t and t star.
Thank you.
Yeah, so that's just crossing. Okay. So we perform find minimum gamma 3 with this imposing unitarity in this way, and we would find that, for instance, gamma 3 is greater or equal to minus 1 over 768. This is what you would find numerically. So you perform your experiments, so let me give you some flavor of how the numerics will look like. Okay. So you do find minimum gamma 3 varying your A con N, and your ansatz will depend on this parameter N. So as you increase the size of the ansatz, okay, so this N, and this is the minimum gamma 3 that you find from the numerics. So as you increase the size of the ansatz, you will get some points here, and eventually you will converge somewhere. And in this case, the result is this minus 1 over 68, which numerically is something like minus 0.0013.
Question.
Yeah.
Is this going to do on the laptop, or do you need to put it on a cluster?
So this can be derived analytically. It can be derived analytically using the dual, so not doing a primal search, and you can do it on your laptop with primal. So this gamma 3 you can really find it in many ways. But yeah, this is like enough. Your laptop is more than enough for this gamma 3. So depending on the time, I have a proof for this gamma 3. I think I have half an hour.
Yeah, 35 minutes.
35 minutes.
Plus question.
Okay. Okay, so let me give you the analytic argument for gamma 3, but before giving the analytic argument, which is just complex analysis, let me compare this number that we get with the lattice data. Okay? So these are the lattice data, for instance, for SU2 groups. So they measure this gamma 3 correction looking at the energy levels in SU2, and they get some gamma 3 which is like it's negative but very small, and it's within our bound. Right? And the same happen for SU6, but it's okay, it's a little bit positive. Okay, so our bound this. But now let me make an observation, right? So the observation, and this is the thing that you have to be careful when you use like positivity, right? So the observation is that now, let's go back a little bit, and let's imagine that you neglect this IR subtraction, which is related to IR cut. So if you neglect this IR subtraction, so neglecting the log, you could write a simple dispersion relation for gamma 3 of this form. 2 over pi, imaginary part of t, s to the 5. Okay. Okay. Yeah. So let's say like this, but generally you want to put some lambda here. Alright? So if you start from 0, okay? So if you start from 0, this tells you that it's positive, and then with this very non-conservative cutoff, you would get that gamma 3 is greater or equal to 1 over 384. Okay? And this number, for instance, is incompatible with the lattice numbers. Alright? So then you introduce a cutoff, you can play this game to put up a little bit gamma 3, to push it a little bit up, but you see that you have to be careful, because if you do not, if we include these IR logs, as we are doing in this case, then we get a bound that is directly compatible with the lattice data. But if you don't, then you have to play with this cutoff, and this can be a little bit dangerous. Okay? So this is the reason why we want to do the full non-perturbative bootstrap. Okay?
Question? So on the gauge theory side, if you consider a larger limit, what is gamma 3?
I'm not sure people have, so they consider SU6, but I don't recall any estimate for a higher end. So people haven't tried the,
I see.
yeah. But in D equals 4, okay, not for this quantity, but for other quantities they did. For instance, the story of the mass of the axion in D equals 4, so there they can do this large extrapolation.
I see.
Yeah. Okay. So before moving to the third point, let me give you an argument why this gamma 3 is greater or equal to this fun number. And the argument is really complex analysis. And it's related to the so-called Schwarz-Pick theorem. So let me write to you here in this very simple proof, so the Schwarz-Pick inequality. Okay? So what we do is that we construct out of the S matrix. So the S matrix is this function that maps the upper half plane to the unit D. Okay? So we construct a functional of this form. Depend on an additional point W. Okay? And we take the S matrix and we do S in Z, S in W, where these are two random points in the upper half plane, and we divide by 1 minus S of Z, S bar of W, like this, and then, okay, this we don't need it anymore. Then we divide by this factor here, Z minus W, or Z minus W bar. Okay, so why consider this functional, which looks a weird function? This function has very nice properties, because as the S matrix, it's still analytic in the upper half plane, in the UHB. Okay? In the sense that even when these 2 points coincide with the boundary, and this would give like a singularity that is cancelled by this difference on top. So this is never singular, this functional. And it's bounded by 1 on the real axis. Okay? So I'm telling you, but it can be easily checked that it's bounded by 1. Okay? So if we take this functional that is built on, it's a function of the S matrix, okay? Take this function, we can apply the maximum modulus principle. Okay? And then claim that this function is bounded by 1, not only on top of the real axis, but everywhere in the complex plane. Okay? Now, it turns out that if you expand this functional in this direction, okay, in the imaginary direction, and you use the low energy expansion of the amplitude that I erased. So if you use the fact that the S matrix at low energy behaves like 1 plus IS L square plus the dot dot dot. So if you use the low energy expansion, okay, and you expand this function along the imaginary direction, right away you get something like an inequality of the form. This functional evaluated on the imaginary axis is equal to -1 plus, and you get this very nice number, 196 plus 8 gamma 3 xy plus dot dot. Okay, where ix and iy are simply these points that are moving on the imaginary axis. Okay? And requiring that this in absolute value is more or equal than 1 implies that gamma 3 is bigger or equal than this number. Okay? So it's just a simple application of this Schwarz-Lamb inequality that you can iterate and derive bounds on higher order Wilson coefficients. Okay? Okay, so now, so this is what I wanted to tell you about non-perturbative bounds versus positivity.
Would you construct another kind of S?
Yes, you can iterate it. So if you iterate it, you get like an infinite set of inequalities in principle, and using all of them, you can really, so what I put, okay. So this gamma 3, if you want, it's just one of the parameters. Then you can have like a gamma 5, gamma 7, you have infinite of them. So if you use these iterative inequalities, you can really find the full, iteratively, the full infinite dimensional space of this.
And this S was not pulled out of a hat, there is a systematic way to
Yeah, it's not, it's very, it's the statement of the Schwarz-Pick inequality. So we knew already this S, and then we just iterated it, and we got like all these inequalities. Yeah, now behind there is some beautiful mathematics. Okay, so let me, so this concludes the second part of the weak coupling. So how we can access weak coupling using the Bootstrap and how we can bound optimally Wilson coefficients. And now let me move to the more Fino-oriented part, which is, so I try to convince you that we need to use the non-perturbative unitarity from the optimal bounds. And the other thing that I also try to convince that non-perturbative unitarity what we need for when we consider quantities that are physically interesting, all right, where we need subtractions. So now we want to take our non-perturbative bootstrap and introduce a concept of a cutoff of an effective field theory, right? Because still we want to study not the space of the all non-perturbative S matrices, but the space of the weakly coupled S matrices, right? And this is the very work in progress part of this topic. Okay? Is there a question?
Can I actually ask a question about the lattice data?
Yes.
So there's SU2 and SU6. This is 2 plus 1 dimensions, right?
Yes.
Is there lattice data on U1 this year? Just a billion?
Just a billion? Yes, but they are not published yet.
Okay. And is it closer to?
It's close, actually, so I didn't even hear the talk. Someone told me that in the talk, one of the authors of this paper are measuring gamma 3, and it's very close to the lower bound that we find. It's very, very close.
Yeah, that makes sense, because it seems that as the n goes down, gamma 3 goes down as well, so maybe for U1 and 2.
Yeah. But for us, it's not so great news, because as I will mention in the conclusions, like we are trying to include multi-particles to improve these bounds, but if there is already a physical theory that already the 2-to-2 bounds, then it's a, okay.
I think there are some results for the Z2H theory,
Right.
it's bounded.
Yeah, that's what, yeah.
Okay.
Exactly.
Sorry, so for the Z2 gauge theory, it does satisfy the bound?
Yeah, it's very close.
It's very
close.
Okay.
Yeah, you probably saw the talk that I didn't see.
The one into 100 years of ice.
Yeah, exactly. Thanks.
So they did Z2, not U1.
Yes.
Z2. Okay, so I misunderstood.
Yes, Z2H2.
Okay. Okay, so you want the Okay. Okay. So what is the idea here? Alright? So the idea is that we want to include the imaginary part, but we want to keep everything weakly coupled. So the nice thing that you can imagine to do is just to, so this is like as a function of S, this is the imaginary part of the amplitude. Okay? And in the optimistic positivity setup, what we say is that the imaginary part is 0 up to some lambda, and then we make it fluctuate freely. Okay? So we want to do a little bit better and let the amplitude to have some small imaginary part. But how define this small is, so I will give like a couple of prescriptions, but this is the part where things get dirty, okay? Yeah, so this is the part that we need to be careful with. But let me tell you first in 2 dimensions, because now dimension is even more, a little bit more complicated. So in 2 dimensions, the prescription looks simple, all right? If you think about the amplitude in a dispersive representation. So I can write a dispersive representation for the amplitude. Okay, so my space of amplitude can be thought as given by this formula. So like our net subtraction constant. So now let me say that now I want to look at the gap. So I want to put a gap. Before it was gapless though, so now I want to put a gap. So there will be some integral from 4n squared to infinity, and the discontinuity of the amplitude, and then we will have some kernel that I will write only once explicitly, and never anymore. Z plus S that goes to U, such that it's crossing symmetry. And here you see that the amplitude, indeed, it's simple, it's a function. Once you specify the discontinuity, okay, this is what is from installing. You specify the discontinuity, the subtraction constant, then you get all the amplitude. So what we can imagine to do is just to define the space of amplitude with some conditions on discontinuity. Okay, so we don't span the full space of functions, but only space of functions that have some that have discontinuity fixed in some region or that obey some constraints. Alright? So the 3 prescriptions, and I will show some plots about them, are, well, first of all, we could really fix the imaginary part. So I could really tell you that the discontinuity of the amplitude is fixed, could be some function, I don't know what to call it. This t in the IR, so this is some known function that I give you, right, which is this profile that we can fix, right, and this for s smaller or equal than lambda. Okay. See that this is not a problem, all right, and it would, so one, the other naive thing that one might think to do is like to fix the full form of the amplitude, not just the imaginary part, okay, but that would be complicated with unitarity. Okay, that would be in contrast with unitarity. But fixing the imaginary part, it's really just, you're looking at the dispersion relation, it really just means to consider a subspace of all amplitudes. Okay? So the real part will still be able to fluctuate and to saturate unitarity and to, well, stay within the constraints. Okay? So this is one possibility. The second possibility, which is less rigid, is just to relax this equality to an inequality. Okay? But it would be still a pointwise constraint. And then the third way to do this, it's the less restrictive one, but it's just to consider some momentum expansion of this discontinuity. So basically integrate this discontinuity in this region from 4m squared to lambda against some kernel. Disk T times k, and require that this integral is more or equal than the integral of our guess for the discontinuity times k. Okay, so then you can choose some subset of kernels and impose many of these inequalities if you want. Okay, so these are the 3 ways in 2 dimensions. Now, before showing the plot, let me just mention what happens in higher dimensions. Okay, so here it's simple because all the data depend on this continuity that you can write, that you can draw on a graph. Okay, so it's very simple. You have in mind that you can just fix this imaginary part and then everything else fluctuate and unitarity. But in higher dimensions, and this is something that we are still exploring at the moment. In higher dimension, the amplitude schematically depends also on the double discontinuity. Okay. So while this quantity can be fixed at low energy if you want, okay, in the same way as one can do in 2 dimensions, for the double discontinuity, this is not clear how to do. So for the time being, the only point I will show you. So in higher dimensions, you would have in principle a profile like this for the double disk, with support in the calculus region. This is calculus. So what we are going to do is to really, so first of all, approximate this calculus in a very rough way, and then set to 0 this double discontinuity by hand. Okay. This is so I'm not going to show it with formula, but let me tell you by word. Setting the double disk 0 in this region and keep it free in the full calculus region. This is associated to multi-particles, so this is really full multi-particles. Okay, where we keep it different from 0. Setting it to 0 here, it's a way to make the higher spins very, very weakly coupled. So basically, keeping a single disk would mean to keep like the spin 0, imaginary part, but setting this to 0, the double disk in this region would amount to set all the higher spin imaginary part to 0. So for spin greater than 2, you set it to 0. That you can see, it's a very strong constraint, but at the moment we don't have a nicer prescription to keep these higher spins weakly coupled. Is it clear? Okay. So, this is the last part. So now let me show you some plots.
It will stop.
Stop. Huh? I think it will stop. Okay. Yeah. So, okay, so this is what we would like to do at some point. So where we want to go. So it's just the list of all the operators that I mentioned at the beginning of the dimension 6 operators at LHC, and we would like to bound them all, but okay, we start with only one of them, CH, at some point. And okay, as you can see, those are all compatible with 0, and that's why we don't have big announcements that new physics has been discovered. Okay, but yeah, we want to bound these quantities in principle.
Which one is CH?
CH is hidden because CH rescales the 3-point function of the Higgs, So actually, it redefines all this coupling simply. So you have to extract it from a global fit of this data. So these are even nicer Wilson coefficients. Okay, so let me tell you how these constraints on the imaginary part work. All right. So here we are considering the space of non-perturbative amplitudes in this figure here, defined by C0 and C2, which are the value of the amplitude at the crossing symmetric point at the second derivative. Okay, so we have some gapped scalar, and we'll look at this space. So this space can be found analytically also. And it has two types. One is the free boson, and one is the free fermion. Right? And if you look at the extremal-S matrices along the boundary, you will find all sorts of non-perturbative S matrices. All right? So this is not what we want to study, for instance, if we want to study weakly coupled effective field theories. Okay? So what we do is that we use one of these arc variables, okay, that have been introduced in this paper by this gentleman, okay. So we use this arc variable, which is just the integral of the imaginary part against some one of these kernels, okay. And we require that the true value of the second derivative minus this arc divided by, okay, normalized in units of the second derivative is smaller or equal than some number. Now, why we do this? Because this arc variable, when I set the cutoff to before, coincides with second derivative. Okay? So A2 is equal to C2 when the cutoff is 4. So when I push the cutoff away, the two differ, and I want to impose an inequality. So this is a way to squeeze the imaginary part using some integrated kernel. Okay? And the effect of this constraint is already nice because it really shrinks the whole region to a very small region concentrated around the free theory, okay, the free boson, which is the effective field theory that we have in mind when we input this this arc bounds. Okay, we could do the same around the free fermion. Okay, we did around the free boson, we find the region around the free boson, and of course this region will depend on these parameters, on the cutoff and on how small you want the imaginary part. So this is the pheno part of this problem, in the sense that we need to take this number from experiments. Okay, so we'll take lambda 1 TP when we want to compare with the LHC. Alright? Okay. And these are different prescriptions now. Okay, so these are the other two prescriptions that I mentioned. Okay, so if we impose that the imaginary part is smaller than some form that is inspired some analytic solution in 2D, okay, this blue region shrinks to the orange one, and one may wonder why this is better. Okay, so so this is the effect that we get, and actually this is slightly better because if you look at the extremal-S matrices along this bound defined by this inequality, still you would find stuff that look non-perturbative, okay, that don't look weakly coupled. So this condition, it really squeezes in the region where you would expect to find weakly coupled theories. Okay, so it squeezed to a nice region. And then the most restrictive one is really the one where we fix the imaginary part. So we really fix it, okay, up to some cutoff, and then we let it fluctuate. And that region, it really squeezed to a line that is not a line but can be rescaled and rotate. It's just a scale. It's just a very squeezed region. Okay? And those are really the effective field theories where one loop is enough to describe the physics up to the scale lambda. Cannot even fluctuate. Okay, so it's very restricted. So it's your taste. I mean, if you want to trust this or this, we still don't know. We still don't have like a good reason to trust one or the other. But I prefer it.
Question?
Yeah.
Is this tangent the same original non-perturbative tangent, or somehow it cut?
It's the same.
It's the same.
Is the same, yeah, because even in the non-perturbative plot, when you are very close to the free boson theory along this branch, the theory looks, the UV completion is like some resonance very far away in the complex plane. So it really is, it reminds a particle that you are integrating out, and you get a Gaussian effective field theory. Right? So in higher dimensions, we can do the same. Alright, so this is like harder to get, cannot be, yeah, this you cannot get it analytically yet, but this is space of gap theories in 4 dimensions. Okay, so this is it. So here now I'm in the singlet case. I'm not showing the plots for the O4 case where you have this dimension 6 operators. This C2 is the second derivative, would be like a dimension 8 operator. Okay, so like a higher order operators. And this is C0 is the quantity that you need subtractions to bound. So this is not bounded by positivity, but the number to the unitarity gives you like some sharp bounds, more or less sharp. And this is the space. So this would be the space of all allowed theories in 4 dimensions. But again, we can go along the boundary and realize that the theories that saturate this boundary are very non-perturbative. Right? For instance, if we are on this segment, we have some spin 0 dominance, but as we go to the stronger coupling, the spin 0 becomes strongly coupled. Okay? So things look perturbable only around the free theory, and then there is this cusp on the other way around that is the maximal interacting theory in 4 dimensions, where the higher spins are maximally excited. Okay? So we have this picture. But this picture, if you want to get phenomenological bounds, is useless because we need some way to zoom in this region. Okay? So, and this is the last plot I'm going to show, and then I'm going to conclude because my time is up. Okay? So, in a higher dimension, as I told you, it's harder, but we can do the same. We can fix the imaginary part of the spin 0 to be the one that you compute at one loop in a gap theory. All right? And then set the discontinuity equal to 0 in this region to make the higher spins not interacting at all. Okay, and this is with some Nmax that is still not optimal. It's some resolution of this region with a couple of theories. Okay, that if you look in the original plot is extremely small and concentrated around the field. Okay. Okay, so these were the results I wanted to show. Okay, and now let me go to the conclusion. Okay, so we are doing all this effort to match, to bridge positivity with Bootstrap, but not just because we want to compare the data, but also to compare with the experimental data. Okay? But, so the lesson that we learned here is that we need to impose additional constraints if we want to get smaller bounds that are compatible with effective field theories, or if even we want to get two-sided bounds. Okay, we need to impose more conditions. So one thing that we are doing right now with Pedro, João, and Alexandre is to consider the effect of multi-particle. Okay, so this is one thing that we are doing. Multi-particle, and we are considering multi-particle in the setup of the flux tube effective field theory. So we have our nice gamma tree, okay, that with only 2 to 2 extends from this number up to infinity, okay, and we would like to improve the bounds. So we can add to the 2 to 2 amplitude, we can also add this kind of processes, okay, 2 to 4, and then so on. Okay, and try to perform the bootstrap. I don't have time to tell you how, but we can do it. But the problem is that it seems that the bound does not really change. This is confirmed by this Z2 gauge theory, right? But okay, nevertheless, this is something we are trying to do, and maybe gamma 3 is not the right Wilson coefficients sensitive to particle production, but there are other Wilson coefficients. Okay, this is something. And then the second lesson is that one needs to introduce a concept of gap. Anyway, a gap in the imaginary part. Okay, and that's what I tried to do in the last part of the talk. And if you use some prescription to input this gap, So to bound the imaginary part, then even in this example of gamma 3, you see that some upper bound appears. Okay, so there will be some upper bound here that will depend on the cutoff. Okay, and perhaps, so I don't know the answer to this question, but perhaps this is the only way that we can really use to put two-sided bounds of this Wilson coefficient. So otherwise, I don't see any other at the moment, any other way. So I will stop here. I think it's enough.
Can you say something more about this Carpus curve? You mentioned it, but then in the end, did you show something in the plot? Or?
Yeah, but it was the last. It was the last slide. So yeah. So let me say. So you see perturbation theory at one loop. So if you like a gap scalar at one loop, okay, perturbation theory that tells you that discontinuity here is just spin zero. So if you work at one loop, you can fix the single disk, okay, but you don't know anything about the double disk. But if you trust perturbation theory, let's say in the region below the gap, okay, you can set this to zero. And this is analogous to set to zero the double discontinuity in the Steinman shadow region, right? So this is like the region where you want to set it to zero. But the issue is that you don't know anything about this this region, which is basically, if you want, a fixed S, but large T, positive, both positive. So if we could input some asymptotic behavior of the amplitude in this region, then we might have under control the higher spins here. Okay. Yeah, so at the moment, setting it to zero, the effect is that all the spins higher than 2, for S smaller than the cutoff, have the imaginary part set to zero, so we cannot unitarize them. But if you turn on a little bit this double disk, then you can. But you need to impose additional further inequalities.
So that forgot something big. The double disk should be zero or not there?
No, the double disk should be zero in this region.
And also in the region below the white line?
Yeah, below the white line it should be zero.
So why are you imposing it to be zero inside of the white line?
Because, okay, so let me write just this point. So, because the imaginary part of the higher spins, okay, is given, so for S smaller than lambda, is given by the integral of the double disk with some generalized leisure, right? So if we are in this region, smaller than lambda, we are basically, the imaginary spin is just given by the integral of the double disk in this sector here. But if you keep it free, this double disk can fluctuate a lot and give like a huge imaginary part to the higher spins, which is something that instead you don't want to do in the effective field theory. So the sharpest thing you can do is just set to zero the double disk. So this is zero, right? And the second thing is to impose some inequality on the double disk, so to bound it all in this region. But then that's enough to get weakly coupled theories. So you don't need to bound it in the full multi-particle region. Notice that this region is also interesting because this is the region where you have like Mahu positivity. So there is some additional positivity that actually is violated in our, so it's something, it's violated in our boot, and maybe we can impose this Mahu positivity in this region also. But at the moment I'm running with zero double disk in this region and support only there, or with this equal to zero. Yeah, there is something else that we could impose. So, you know.
What is that, Mahu positivity?
It's the fact that the imaginary part of the amplitude converges in the large Lehmann ellipse. So you can cover a little bit of the double discontinuity part, and positivity extends a little bit more. So even in the t greater than 4 region, right? So it extends in some curve that is like here. This is reviewed in the paper by Sashi, Miguel, Amit. Very nice. Yeah. Yeah.
So how does your story change if I add adjoint matter? For example, make the the three-dimensional gauge theory supersymmetric. So how would what's your expectation on how gamma 3 would change, for example?
Right. I mean, it's a very interesting question, but you
And
can-
are there are there also results available for those cases? Sorry, this is a series of questions.
Yeah, no, I mean there are no bootstrap data, but you see, once you have like the effective field theory and the low energy, then it's simple to set up the bootstrap just to get the balance. So there are no words about it, but yeah, in principle can be done.
But let me just make sure, your bound will still apply, right? If I just add adjoint matter.
So let me think. If you add the adjoint matter, I think so. In the sense that if you don't specify something about the UV theory, then they should apply, because these are very generic and very
Yes.
bounds.
Yes.
Yes.
Thank you.
More questions? If not, let's thank Andrea again.